No, I thought we were doing this physics stuff
Yeah, so
today. Are we doing that or something else?
let's come back to it some other time because today time is short. So yeah,
Hello.
physics takes.
Hello.
You cannot hear me? Hello, can you hear me?
Yes.
Yeah. Okay. Chances it's no problem. Okay, so yeah, let's keep physics for another day. Physics takes time and it's beautiful, but yeah, that's not our main job. So, anyways, so we'll assume that I mean this is the replacement for probability distribution for whatever reason. There are good reasons behind it, but we'll just assume them as a black box. Okay. So, what other things we can do? So let me. So this is composing.
Pranab, so physics means you'll do it from quantum harmonic oscillator point of view and then
No,
come
no,
to
no,
finite
no,
dimensional?
no, 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 not
Okay.
at all. So composing Hilbert spaces and tracing out, which is the replacement of marginal probability distribution. Okay, so let's do this. So last time we saw that. Just a second. Yeah,
Pranav isn't talking, right? There's some issue with my connection, I think.
okay, yeah. So let's start. So we will see how to compose Hilbert spaces. Okay, so what do you mean by that?
Pranav, just 1 second. So last lecture you said that today you will be discussing the physics aspect of all
Yeah,
this. Why?
but we don't have that much time, so we will do the physics other day. It's independent of what
Okay.
you're doing, right? I mean, you can always assume it as a black box and go ahead. I mean, the point is there are good reasons for adopting this formalism.
But we will do that at some point, right? I was kind of
Yeah, I
looking
mean, in a
forward to
hand
it.
wavy level. I'm not going to
Okay.
really do physics.
Okay.
Okay. So if you really do physics, then I mean, that requires independent study. Okay. Yeah. So let's. Okay. So what do you mean by composing Hilbert spaces? So let us go back to probability theory. So let us say we have a sample space. Okay, so we have one sample space. So we have one sample space X. Sometimes we call it register X, and we have another sample space Y. Now, we want to talk about the joint sample space. So joint sample space is, we know, X Cartesian product Y. So that's defined to be X Cartesian product Y, right? So, and the logic behind it is that what are the sample points, the elementary whatever the events. So the sample points are elements little x of capital X or elements little y of capital Y. when you're talking the joint sample space, our elementary events will be pairs of the x comma y. So the natural set to model them with is x Cartesian product y. So now, what will be the quantum analog of this? So this is the first place where some non-trivial definitions will come in. So in quantum, instead of sample space, the corresponding thing was the vector space or the Hilbert space. Okay? So we'll use the jargon Hilbert space because that's used over time. So these are just finite dimensional vector spaces over the field of complex numbers. So same notation, x, y hat. So now what is the joint Hilbert space? Okay. So this is defined to be the tensor product space of x and y. So this is a symbol, and you see in many of my earlier slides and works, I deliberately use the tensor product symbol to even denote x Cartesian product y. Okay, I mean, though I was just working probability distributions for the joint sample space, I used this. This was basically to remind you and ease you of the quantum notation. So this is a generalization of space. Okay. So Hari, have you done tensor product in your linear algebra course?
No, no, no.
Sorry, no.
No, no, no.
Okay, so then let's do it now. Okay, so this is a slightly abstract concept. It will take a little bit of time getting used to it. Okay, so let's see. So my Hilbert space X. Okay. So it's some finite dimensional space. So I can talk of an orthonormal basis for it. So orthonormal basis, you know, right? I mean, it's a basis set of vectors which are linearly independent and span the entire space X. And orthonormal, first of all, means each vector is unit length. So, I mean, you know what is the length of the vector? Like you take the dot product to itself and take the square root. So it has unit length, and any two distinct vectors in the set are orthogonal. Okay. So let us say I have X, and of course, the vector space X can have many orthonormal bases, right? I mean, even if you look at R3, like you take any three perpendicular vectors, they'll form an orthonormal basis. So, but let's fix one of them. Okay? So X, so I'll fix an orthonormal basis. Okay? So X can have other bases, which is not orthonormal, but we usually will not be looking at those things in our quantum information study. Okay? So fix an orthonormal basis. So let's give names to those vectors. I'll call it x1 dot dot xn. So m is clearly the dimension of x. Okay. And as I said, I fix this set. There are many sets possible. Choose one and fix it once and for all. So this becomes a special set which has a special name, which I'll call the computational basis. By the end of this lecture, it will become clear why I've chosen this. Okay. So this is a special basis. Okay. Amongst all orthonormal bases, I have chosen one special basis, which I'll call computational basis. And similarly for y. So for y also, I will fix the computational basis y1, yn. Dimension of y can be different, right? So this is also computation. Okay. Now, so I'm going to write something which is may seem very obvious and trivial, but please bear with me because that obvious and trivial thing will suddenly look non-trivial when I go to tensor product. Okay, so I'll say that X is the span of x1 to xn. Everybody understands. So what is span? So I'm going to be very pedantic. It is the formal linear combination with emphasis on the word formal. So the span of this set is the set of formal linear combinations So this is the set.
So I have a slightly abstract question, maybe slightly looking ahead. This X and Y spaces, the vector addition can be different, right? In both the spaces. That doesn't matter when you take the tensor product.
Yes, it doesn't matter. Okay. Okay, so let me explain. So these are complex coefficients. And similarly, I can write y as the span y1 to yn. Okay. So again, these are formal linear combinations. So now,
Pranam, have you written alpha 1 to alpha m does not belong to complex? Or it's belong
no,
to
it belongs to
complex.
complex. Belongs to. Yeah, I think. I don't know. Yeah, belongs to complex. Looks like does not belong. I don't know what I was thinking. Oh, what happened to this? Something happened to my pen. Okay, now it's fine. Beta and yn, beta 1, beta n belong to complex. Okay. So, I mean, this doesn't look anything new, but here the emphasis is on the word formal. So what does formal mean? Suppose you knew nothing about the vector space X. Somebody gave you this set X1 to Xn. Said, okay, these are some fixed vectors. I'll say, okay, how do I make sense of the vector without knowing the vector space? So this is where the abstract thinking part comes in. So let us say these are some objects. I mean, I will not look into structure of the objects. I assume that these objects, these thingies are given to me, X1 to Xn. Then I'm going to write expressions on paper, which look like alpha 1 x1 plus alpha 2 x2 dot dot alpha m xn. I have no way of actually doing this addition because I know nothing more about x1 to xm other than the fact that this is some set. These are the labels of the elements of the set. Okay, no more structure I know. So I'll be looking at all objects, okay, all expressions on paper that I can write of the form alpha 1 x1 plus alpha 2 x2 dot dot alpha m xn. I claim that the set of these objects, okay, the set of these expressions that I can write on paper itself forms a vector space.
So I can always say that no, because this is finite dimensional. So it is isomorphic to Euclideans and
surely you can always say that. I mean, but I mean, the first time you hear it, it's kind of abstract.
Okay.
Okay, remember, I mean, you are not hearing it for the first time. You did it in your linear algebra course because I took that course. Okay. Yeah. So, but now I have to do those things here. Okay. So, Hari, are you on board?
Yeah, it's fine.
Yeah.
Like we did something similar in our course also, like this abstract things. Yeah.
Yeah, good. Yeah. So, I mean, it will, you have to draw on those memories. Okay. So, I claim that these formal linear combinations itself forms a vector space of dimension n. So, okay, if it forms a vector space, I have to show how to add them. So, let us say I take this formal expression alpha 1 x1 dot dot alpha m xn, and I add it to another formal expression alpha prime 1 x1 dot dot alpha prime m xn. So the definition of this addition is take alpha 1 plus alpha 1 prime. So this is an addition of complex numbers, which you know how to do. Multiply this complex number by the symbol x1. So this is the formal operation. So similarly, alpha 2 plus alpha 2 prime multiplied with x2 dot dot alpha m plus alpha m prime multiplied with xn. So this is another formal linear combination that I've given you. Okay, and this is the definition of adding two formal linear combinations. Now, similarly, scalar multiplication, like if I have formal linear combination alpha 1 x1 plus dot 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 alpha m xn, I want to multiply it by some gamma, complex number gamma. This is the formal linear combination. Gamma times alpha 1, that's a complex number which I know how to evaluate. So gamma times alpha 1 multiplied by x1 plus gamma times alpha 2 multiplied by x2 dot 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 gamma times alpha and multiplied by x. Right. So I've defined the two basic operations of a vector space: the addition of vectors, multiplying a scalar with a vector. Right. All at the level of formal linear combinations. So I suppose this is clear to you now, Hari. Yeah.
Yes.
Yeah. Okay. Good. So then you can check that once you have this formal linear combination, these expressions on paper, all the axioms of vector space will be satisfied. So this addition will be commutative, and this addition of formal expressions. This addition will be associative. Then the scalar multiplication will distribute over the vector addition at the level of formal expression. All that will go through. So this is indeed a vector space. Now the only thing left to check is that this is inner product space. So now I have to define what is the so I'll say that the vector addition and scalar multiplication defined formally. Now to just define the inner product. Okay. Should be fairly clear now. So I have to define what is the inner product of one formal expression alpha 1 x1 with another formal linear combination alpha prime 1 x1. So you can guess what it is. This is defined to be, yeah, Hari, you can tell me.
Wait, so these x1s and xm's are same in both these
Yeah.
vectors,
So yes. So when I'm taking formal linear combination of these x's only. So every formal expression will have the same x's, but the alphas are different.
And then it will be alpha 1 prime plus alpha 2 prime plus.
There's also complex conjugation.
Yes. Yes.
Right? So it is alpha 1 star, alpha 1 prime. Okay. So I'm doing complex conjugation in the first argument. That's a matter of convention, but the convention that we follow in physics and in quantum information theory is complex conjugation in the first coordinate. So this is how it's. So this is a certain complex number that you can easily see, and this is defined to be the dot product, the inner product of two formal expressions. And again, you can check that this inner product satisfies strict positivity, or the dot product of a formal expression itself is greater than or equal to 0, and it is strictly greater than 0 if the formal expression is non-zero. Yeah, the zero formal expression is all the coefficients are 0. Okay, and the formal expressions with different coefficient alphas are treated different because they're different expressions on paper. Okay. So you can very well see that what I'm writing down is a bad way of writing down the vector space Cn, the set of m tuples over complex numbers, right? Essentially all the information is captured in the m tuple of the alphas. Okay, but it's just a bad way of writing that, but it becomes useful for defining the tensor product. Okay, sure. Now you can also check that with this definition of the inner product, then yeah, what else do you need about the inner product? The inner product is a bilinear form. So if I put one fixed expression here and I put the sum of two expressions in the second coordinate, then the inner product will distribute over that. And if I do the reverse, I put the sum of two expressions in the first coordinate and the fixed expression second coordinate, then also will distribute, but then there is a complex conjugation. Well, it will distribute for sure. Yeah. The same thing for the scalar multiplication, but if you're doing scalar multiplication on the first coordinate, then there'll be a complex conjugation. All this is easy to check from this this definition of the inner product. So great. So with these properties, the set of formal linear combinations becomes the inner product space. Okay, so that's what we have learned from this exercise. Set of formal linear combinations. Hilbert space, inner product space, Hilbert space, same thing. Okay. And whatever I did for the alphas, you can build another vector space for the betas. You can also check that if I started off with n such x's, right? So this space is of dimension n. Okay. Then you can also check that. Okay. So remember, I mean, the motivation was the x1, x2, xn forms an orthonormal basis. So you can even check that the dot product of xi with xj is equal to 1 if I is equal to j and 0 otherwise. So this is by the Kronecker delta sum delta ij. Okay. So when I write an expression like xi, this is a formal linear combination which is zeros for the other xi primes, and the coefficient is 1 for the given xi. This is just a shorthand for my formal linear combination, and easily you can see it satisfies this orthonormality property. Okay. So any questions so far? Okay, good. Not. So now we know how to write formal linear combinations, and we have seen how formal linear combinations form a Hilbert space. So now I can define tensor product. So X tensor Y is defined to be the formal span of this set Xi tensor Yj. Okay. I equal to 1 to n and j equal to 1 to. Okay. So what do you mean by that? So I had this set, this abstract set x1 to xm. I had the set y1 to y. Form a new set of the cardinality of the new set will be m times n. Okay. So the new set is just the Cartesian product. Okay, but I'm writing it with this special tensor symbol to remind you that we are going to build a tensor product very soon. Okay. So take the Cartesian product of the two basis sets. Okay, that's the idea. And now take the formal span of this set. So this is a Hilbert space for sure. Okay, and this Hilbert space is called the tensor product space. Okay. So this is why the definition is a little abstract. The tensor product space is itself defined as an abstract formal span. Okay. So I can
Pranab,
I can
weird
immediately
question. So
yeah, so finish. You can keep asking. So I can immediately see that the dimension of x tensor y is a product mn, right? Because the orthonormal basis is this Cartesian product of the two basis sets. Okay, it has carrying. And again, because it's a formal span, this is an orthonormal basis. So the orthonormal basis for x tensor y is this set. Okay, and there's a name given for this this basis. Okay, so this basis is called computational. Remember, X was called the computational basis of the Hilbert space capital. So this is the computational basis of the Hilbert space X tensor Y. Okay. Yeah, Shantan, ask your question.
yes, so I mean, in formal math, all this is defined by this universality property or the commutative
Correct.
diagram or something,
Correct.
right?
Yeah. Correct.
So as far as I know, I mean, you can define tensor product in many ways, but there are two different definitions. One is via first you go to the Cartesian product and then you essentially imbue it with this basis property that you just said. That's this universal map or something. But there is another kind of product which I remember, which I think it's called the wedge product.
No,
is
wedge
that
product will
different
come
from
later.
this?
No, the wedge product will come later. So those are the subspaces of the tensor product. So you have to define tensor product before. Okay.
Oh, okay.
So
Okay.
There's the wedge product. There is the, I mean, maybe better than the symmetric product and alternating product. So these are subspaces of the tensor products. You can also define them directly via similar universality properties. That's okay. But yeah, they're better. I mean, nicer to be viewed as subspace of the tensor product.
Yeah, visualization. This is much better. Yeah.
Yeah. So as I keep saying, I'm sure you've heard this from me before, but maybe Hari is hearing the first time. So in computer science, we have to do double the work of mathematics. Okay, so mathematicians often will define the tensor product in an abstract way, which Shantan was talking of the universality definition. Okay, but then if you actually have to do calculations on pen and paper or in the computer, okay, you need this explicit hands-on definition. Okay, so often mathematicians do not bother so much with explicit hands-on definition. In computer science, we need explicit hands-on definition because we are going to do calculations. Okay, with this. So, and we are going to do, I mean, even computations in a computer simulations maybe. So we need this explicit definition. But on the other hand, at some stage in life, you have to know the universal definition also. Because if you really want a nice mathematical abstract view of what is going on, I mean, if you want really a deeper understanding of what is going on, you do need the universality. Okay. So we have to do, so in computer science, we have to do double the work. I mean, we have to know both the views, the explicit view and the abstract universality. Okay. But anyway, for now, I mean, in this course, I think we will get by just the explicit view of this thing. Yeah.
Is there
So,
any place, I mean, further along when you're doing research, say where, I mean, at least till now I haven't seen, but where the universal view
I'm sure we've encountered it like many times when I mean you have some expression involving tensor products and they say this is equal to this. Okay. I mean, and then sometimes it's not obvious. Then you have to go back to the universal view and say, oh, okay, this satisfies the universal property, so this must be equal to this. There's a uniqueness there. Okay. So these things will arise. Okay. I'm sure they would have arisen, but I mean, but you sort of know the abstract view. So, I mean, you would have just, I mean, read it and understood it. Okay, but if you, I mean, only know this view, then sometimes some like two expressions involving tensor, and they say that this is equal or this is isomorphic. It may be a little bit I mean, maybe a little bit difficult to see if you only know this view. So,
I
yeah.
have a question.
Yeah.
So can it be like simply like in an oversimplified sense, can we understand this like in a vector space, every element is a vector, but like a vector in the sense vector with like n elements, but in this tensor product space, every element is a matrix of m by n size. If it's a particular basis, then we can get some matrix.
Okay. So very, very good question, Hari. So it's not fruitfully viewed as a matrix. Okay. It is fruitfully viewed as a vector of length mn. So, and the reason is that soon we will be doing so-called tensor product or Kronecker product of matrices. Okay. And if this whole theory has to make sense, you better view this as a tuple of size mn, okay, not as a m times n matrix. So
I do have a comment here. I do have a comment here. Shall I say?
Yeah.
Yeah. So this matrix view, this is sort of fruitful in some other parts of CST, so as far as I know. So there's this thing called a multilinear map. Okay, this is in fact one way of defining tensor product is what dual of bilinear maps or something. So, but that is very, very abstract, and you can do it that way. But when you're doing quantum, it's much easier to look at. I mean, you're not wrong, but it's easier in this picture for our applications.
Okay. Yeah. I mean, essentially, you're going back to the university view. I think. I mean, I didn't really follow it, but I think.
Yeah, I think they're called tensors, like general tensors. I have some very weird name.
Well, so the elements of the tensor product space are called tensors. Okay. So, and there is more about it also. I mean, the word tensor has slightly different meanings in different communities, but anyway, we'll go into different than that. So in physics, there are things called tensors. So they have a slightly different meaning than just elements of a tensor product space. So, but yeah, but I mean, they're related, of course. Okay. So, but yes, at the end of the day, you can say that the elements of a tensor product space are called tensors. I mean, that is always true, whether you're from physics community or maths community. But I mean, the way you deal with them, which aspects you emphasize, are different across communities. But that's okay. So for our purposes, I mean, it is best to think of this a vector in the tensor product space as a MN tuple. So in fact, I'm going to explicitly show you that. So let us say I take an example. I said, let us say I have V in X, okay, and I'm going to write V as alpha 1, alpha n. I said, I mean, really V is like a tuple, and W is in Y. So W is an n tuple, beta 1 to beta n. So now, okay, so I want to define what this means. So I want to define what V tensor W means. So remember, V is an arbitrary vector in X, W is an arbitrary vector in Y. So this is defined to be, okay. So remember, V is a formal linear combination, right? So it is alpha 1 x1 plus alpha n xn. And let me put this formal symbol of the tensor product, and this is beta 1 y1, beta n yn, right? So now I just do a formal operation. So this is formally defined to be summation I j alpha I beta j, okay, xi tensor yj. Right? So once I do this, then I'm done, because this is a formal linear combination of these symbols. Okay? So this formal linear combination is an object in the formal span of xi tensor yj. So that's the definition of the tensor product of a vector v coming from x and a vector w coming from y. So let us see what this picture looks like in the tuple world. So it will be quite easy to see. So alpha 1 to alpha n tensor beta 1 to beta n is really explicit things. I mean, if you're doing some computer algebra package, you'll be working with tuples. So this will be this tuple, as you can see. This is, let me write it in suggestive notation. Okay. So this is a mn tuple, but I've broken up the mn tuple into blocks of size n each. Okay, and the first block I'm telling you is alpha 1 times the beta vector. The second block is alpha 2 times the beta vector, dot dot. The mth block is alpha m times the beta vector. So this is basically alpha times alpha beta j only in the lexicographic orders. Okay, so I first vary over the j index, and then I vary over the I index. So if I use this lexicographic order, then I have this nice expression. It's easy to remember this expression. So that's why it's nice. Okay, so this is a very tuple way of defining the tensor product of two vectors. Is it clear to everybody? Okay, good. So let's go ahead. But yeah, but now comes the important. Yeah, I can hear you. But now comes the important remark. A very important remark. So really important remark. Not all vectors So remember, we had defined the tensor product with X tensor Y. You may be misled into thinking that every vector in X tensor Y is of the form V tensor W. That's not true. Not all vectors in X tensor Y are of the form V tensor W for some V in X, W in Y. Let's see this with an example. Okay. And this mathematical property has immense implications to quantum information, okay, which will slowly become clear as the course proceeds. So let's see. Okay, so I will take X to be C2, the simplest non-trivial space that's around. Y to be C2. Looks like 3 by 2. And I'll take the standard basis vector of C2. Okay, so remember, like there is this vector which I'll call E0 and E1. These are the definitions. The standard basis vector, right? So it has a 1 in one particular coordinate, 0 elsewhere. I'm calling it E0 and E1 because the first coordinate I'm calling the 0th coordinate. So this is a 0th coordinate. Okay, so I mean this becomes useful for computational application. This way of labeling the coordinates, and this is the first coordinate. Okay, so the coordinate numbers go from 0, 1, 2, 3 up to n minus 1. Okay. So I take my preferred basis of X to be the standard basis, and I'll call this the computational basis. In the physics world, they like to call this basis by this symbol, cat0. So this basically indicates the coordinate number where there is a 1. And they call it cat1. I mean, this symbol with a bar and this greater than symbol is called cat. Okay. So this is the jargon for denoting E0 and E1, the standard basis vectors. Okay. So now X tensor Y, by definition, is the formal span of E0 tensor E0, E1 tensor E0. Actually, let me go in lexicographic order. So I first vary over the J index and then the I index. That's better. So E0 tensor E1, E1 tensor E0, and E1 tensor E1. So this is a formal span of this. So let's see what this looks like. So X tensor Y is the formal span of. So this is E0, remember, was this. Then E0 tensor E1, E1 tensor E0, lexicographic order. And finally, E1 tensor E1. Right? But now, I mean, we know how to do tensor product of vectors expressed as tuples. So this is span of, so you can see what this looks like. 1, 0, 0, 0. This is 0. Then 0, 1, 0, 0. 0, 1, 1, 0. 0, 0, 0, 1. So what have you got? I mean, this is something very familiar. So if I forgot about this X tensor Y business and I just took C4, okay, the space of 4 tuples over complex numbers. So, and I said, okay, let me take the standard basis vector for standard basis for C4, then I would have taken exactly these vectors, right? So what does this say? This says that the standard basis for C4 is the tensor product basis coming from C2 tensor C2. Okay. So what I've shown is that as vector spaces, of course, they're isomorphic, C2 tensor C2, but not just that. The standard basis, also called the computational basis, remember? That's computational basis is the computational of C4, okay? Computational basis of C2. Then symbolically, you take the tensor basis. This is the computational basis of C2. Okay. So here is the nice advantage of working with computational basis, and especially taking the computational basis to be the standard basis if you're working with tuples. So yeah, so the tensor product of the computational basis is yet another computational basis. So is this part clear, Hari?
Yes.
Yeah. So now, of course, what are the vectors in the tensor product space? So tensor product space C2 tensor C2. C2 tensor C2 tensor product space. I know it's isomorphic to C4. So I know anything that lies in the span of these four guys lies in the tensor product space. But what lies in the span of the four guys? Any arbitrary four. So actually, the elements of the tensor product space is really elements of C4, an arbitrary four tuple. And not every four tuple can be obtained as a tensor product of two tuples. So that's what I'm saying, and we'll just see it by example. So not every four tuple is a tensor product of two tuples. Okay. Yeah. So if you look at what are the four tuples you can generate by tensor product of two tuples, it will be a strict subset of the set of all four tuples. And here is one such four tuple which is not a tensor product, which you can easily check by a little bit of algebra. So this four tuple, this cannot be written as like alpha 1, alpha 2, tensor beta 1, beta 2 for any alpha. You can check by a little bit of manipulation. This is not the case. So now if you go to the quantum ket notation, so what is this vector? This vector, okay. So it's a linear combination of the first standard basis vector and the fourth standard basis vector. But the first standard basis vector, as we know, right? The first standard basis vector, as we know, is this tensor product, and the fourth standard basis vector is this tensor product. Okay. So what does this tell us? That this particular vector is nothing but 0 tensor 0, ket 0 tensor ket 0, plus ket 1 tensor ket 1. Okay. So this is not equal to whatever, like so the notation is like take any vector v in C2. So to emphasize that I'm taking a vector or a two tuple, I'll put it in ket for any v in C2 w in C2. This you can check that this is the case, and this particular example which I picked out. Okay, so this is a very very important vector. Okay, in quantum physics and quantum information theory. So this is, you've heard the term, this is what is called an EPR pair. Like if you've heard of the EPR paradox, these are the vectors which go into explaining what that paradox is. So I mean, we'll come to all that. Okay. But yeah, so the fact that I mean there is something called EPR pairs and EPR paradox arises from this simple mathematical fact about tensor product spaces, that there are vectors in the tensor product space which cannot be written as V tensor W. So there's a name given to these vectors, a quantum physics name. So these vectors, vectors which do not arise or rather, let me write down clearly, the vectors in X tensor Y which are not of the form V tensor W, okay, are called entangled vectors. So this is a quantum physics name. And why they're called entangled? I mean, it's related. The name is it's related to the physical effects that come from EPR pairs. But yeah, so for example, this is an example of an entangled vector. So in short, entangled means you cannot write it as a tensor product of two vectors. In fact, if you just close your eyes and randomly write down a 4 tuple, it will be an entangled vector. Okay, questions?
Yeah, hello, hello, hello,
Yeah, I'm listening.
hello.
Yeah, Shan, go ahead.
Oh, okay. So, yeah. So this entangled vector, right? So, any entangled state like this. So the way it sort of depends on the basis, on the tensor basis with which you constructed the space. So and I mean, at least this definition was basis dependent. You fixed basis for both spaces, and then you define the tensor space
Yes.
based on each of those bases. So my question is, uh, can one prove that no matter what basis you fix for each of the component spaces, you can never write an entangled vector as a tensor product of those bases?
Surely. Well,
As
I
tensor
mean,
product of vectors in those
yeah, I mean,
those
that's
spaces.
already kind of in the definition. Like vectors which you cannot write as V tensor W are called entangled. Okay. So remember, I'm not talking of computational basis vectors on it. These are arbitrary vectors in X and W. Okay. So, but I mean, let me take a step back and I mean, add more stuff to your question. So the way I define the tensor product space, well, I mean, it was an abstract thing out here. I mean, it was like, okay, fine. I mean, if you start off with two vector spaces X and Y, but I'll say fix a basis for X, fix a basis for Y, I mean, special basis, call them computational basis. And now take the formal Cartesian product of those bases out here, but write it with this tensor symbol, and now take the formal span of these symbols, and that formal span is a vector space. It's a Hilbert space called tensor product. So you may sit and wonder that, okay, but I can take a different orthonormal basis for X. Now let us say X is given to me abstractly, and I can take a different orthonormal basis for Y. So I've changed my definition of computational basis. So that will of course change the definition of the tensor basis, which I mean, a priori seems to change the definition of the tensor product space. So the point is that the tensor product space that you define by using a different basis is isomorphic to the original definition. That's simply because there's an isomorphism. So what is isomorphism? So I started off with this fixed basis x1 to xn. Maybe I take another orthonormal basis, x prime 1 to x prime n. So look at the linear map. So to define linear map, I have to just define its action basis elements. So look at the linear map which maps xi to x prime I. Okay. In fact, this linear map preserves the inner products. These are called unitary maps. Okay. So similarly, there is this is a change of basis map taking you from the x basis to the x prime basis. Similarly, there's a change of basis map taking you from the y basis to the y prime basis. So essentially, there's a change of basis map. Okay, so we will, soon formally write down in the language of linear algebra, how to write down such operators. But you can imagine what is it. So there is a formal change of basis map which sends the xi tensor yj basis to the x prime y tensor y prime j basis, which is the obvious thing. Like xi tensor yj is mapped to x prime I tensor y prime j. Okay, so it's another set of the same size, Mn. Take its formal span, define the isomorphism accordingly, right? So that's it. So the tensor product defined using the two different bases are isomorphic. So we will, not be distinguishing between them in our calculations. We have to fix the basis, as I said, for our calculation ease for concreteness. But yeah, the space is so defined isomorphic. So now the question is, okay, so let us say I've chosen a basis for x, chosen a basis for y. I have a tensor product basis and I define x tensor y, the vector space x tensor. I find the vector in the vector space x tensor y, and I say that, oh, I cannot write it as a tensor product v tensor w. So it's entangled. The question is, if I had used a different way of constructing tensor product by using different bases, will this remain entangled? The answer is yes. Again, because of the isomorphism. That if you change basis for the original spaces, okay, you have to use the change of basis isomorphisms. So you correspondingly get a change of basis isomorphism here. So if a vector which is entangled according to the first choice of basis, its image under the change of basis will be entangled under the second choice of basis. Okay, does that make it clear?
Yeah,
So,
yeah. Sorry.
yeah, so I mean, if you
Yeah, got
sit and work it out. So here it's useful to, maybe look at some linear algebra books where these things are done. Okay, so yeah, so the definition of entangle does not depend upon the choice of the basis. Okay? So the particular coefficients here which arise in this linear combination, that does depend on the choice of the basis, but not the nature of entangled versus non-entangled. Okay. So good. More questions? Okay.
So, what were you saying in the last sentence? Like, if we change the basis by which we have constructed the tensor product, then the entanglement.
No, the definition of entangle, what is
No,
entangled doesn't change,
so
but the coefficients which arise. Okay, so I mean, if I change the basis of C2 here, change the basis of C2 here, okay, then this same vector. So if I look at this image under the change basis, it will look different. Okay, it may not look like 1 times ket0 tensor ket0 plus 1 times ket1 tensor ket. So it will look something different, but it continue to remain intact. That's what I'm saying.
Yeah. Okay.
Yeah, more questions? Okay, so yeah, let's see. Said I have other engagements. Is there some short, sweet thing I can do? Yeah, so okay. So I've defined what is, what do I mean by composing Hilbert spaces? So once I've composed Hilbert spaces, so okay. So classically, I mean, it was the Cartesian product of sample spaces, and yeah, so what did I have? Let's go to the page. So Cartesian product of sample spaces x cross y. Okay. And now the objects of study will be joint probability distributions, okay, on x times 1. Okay. So here now it becomes a Hilbert, so it becomes a tensor product. This is the tensor product. X tensor Y. So the objects of study are density matrices. Okay. So if you want, I'll call them joint density matrices. So what's the joint probability distribution on X tensor Y? So if I, for example, look at C2 tensor C2 giving me C4. So the classic analog is I have a sample space of size 2, let's say whatever, head tails coming from a coin. So that is X. Y is another coin. Okay, and now I'm looking at what happens if I toss 2 coins. So all 4 possibilities are there, right? I mean 0, 0, 0, 1, 1, 0, 1. So an arbitrary probability distribution I can take on these 4 possibilities. So that will be a joint probability distribution X tensor on X times Y. And like in the spirit of entangle, not every probability distribution is a product is a product of marginals, right? So they are kind of like the entangled vectors out there. So there are probability distributions which I cannot write it as a product of 2 probability distributions. So joint probability distribution X times Y. So so the quantum analog is I have this Hilbert space X tensor Y. Take any density matrix. So if the tensor product space is an Mn dimensional space, so the density matrix will be Mn times Mn matrix, which is Hermitian, positive, semi-definite, and has unit trace. And as you can expect, I mean, not every density matrix can be written as a product of density matrix on X times the density matrix on Y. I've not defined what it means to take product of matrices. So that I will do in the next lecture. So that is the tensor product or the Kronecker product of matrices. Okay. But I mean, in analogy with the probability distributions, yeah, the joint probability distribution on X Cartesian product Y gets replaced by a joint density matrix on X tensor Y. So this probability distribution is supported on a sample space of size Mn. This density matrix is the Mn times Mn matrix. Okay. I mean, this was an Mn tuple. This is Mn times Mn matrix. Natural. So I think we'll stop here because, yeah, my next engagements to prepare for that. Yeah. So any questions? No? Okay, so I'll stop the recording.
Pranav, I just have a small question.
Okay. Then will not stop the recording.
So so this discussion might sound a little weird, okay, but usually in like combinatorial problems and such, usually we come up with some scalar quantity which sort of describes the some important property, like for example in a graph you can have chromatic number, you can have independence number, whatever. So I was just wondering, I mean, I don't know if this is true, but in a vector, given a vector from a tensor space, is there some quantity which we can write down which sort of tells me that, okay, this thing is entangled and this thing is not entangled? Because from what you said earlier, what I understood is that entanglement is completely a basis independent property. It's a property of the vector itself. So is there some function on the vector space two reals which sort of tells you that, yeah, this has entanglement and this does not have entanglement?
Sure, there are, I mean, there are whatever, like, what are they called? Entanglement witnesses, I think. Okay. So, yeah, so, I mean, see, I mean, if you're just talking of vectors, that's not so difficult. Okay. So, I mean, you can, given a vector, you can compute its Schmidt decomposition pretty easily. Okay. So, I mean, these are things that, of course, we'll see later in the course. And I mean, from the Schmidt decomposition, you'll immediately see whether it's entangled or not. Okay. So
we can also sort of use this.
Yeah, I mean, you can use this definition and try to solve some equations. But
no, not this definition. I was going to say, I was going to say we can use the this Shannon conditional entropy, right? So if you have an entangled state, then you know that conditional entropy will
yeah,
be negative.
yeah.
So that is one candidate. Are there
That
other
is one candidate.
candidates?
That is one candidate. Yeah, yeah. There are other cases. So for vectors or so-called pure states, I mean, checking whether things are entangled or not is very easy. But once you have density matrices, then you have to first define what it means to be entangled. The definition is a little different. Okay, and then
I think there's also a PPT criterion,
yeah,
a
yeah.
positive
So,
partial transpose.
yeah, but it's not. It's a sufficient criterion, but it's not a necessary criterion. Yeah, yeah. So that leads to other areas of study. I mean, the study of entanglement theory. Okay, so I mean, in this course, we will not go into those areas, but I mean, they are big and thriving areas in their own right.
Okay.
So, yeah.
Take care.
Okay, I have to go now. So I'll see you on Thursday, right?